Welcome to the Deep Sleep Science Channel. Tonight, we're drifting across the strangest places on Earth, where glowing caves look like star-filled skies. Deserts bloom with hidden lakes, and fire burns endlessly in the quiet dark. Some of these places were shaped millions of years ago, while others are still changing right now beneath our feet. Some seem impossible at first glance, like they shouldn't exist at all. Yet every one of them is real. So gently settle in, relax your mind. And if you'd like to support the channel, you can leave a like, subscribe, or share a quiet comment before sleep finds you as we slowly explore these extraordinary corners of our world together. The Richat structure in Mauritania is a giant circular landform in the Sahara, often called the Eye of the Sahara. What makes it so astonishing is not only its shape, but its scale. It is so large and so clearly ringed that it seems less like an ordinary landform and more like a symbol drawn onto the desert. From above, it looks deliberate, almost designed, even though it is entirely natural. The structure is about 45 to 50 kilometers across, which means it is far too large to truly understand from the ground in a single glance. At that size, the eye-like pattern only fully reveals itself from high above, especially from aircraft and spacecraft. That immense scale is part of what gives the place its strange power, because it belongs to both the desert below and the view from orbit. Shuttle crews and astronauts have used the Eye of the Sahara as a visual landmark in orbit. That alone makes it unusual, because very few landforms are so distinct that people circling the planet can recognize them as navigation points. It stands out in the vast tan sweep of the Sahara, like a target, a ripple, or a giant mark pressed into the earth. One reason the place feels unreal is that it looks like a target stamped into the desert, even though it is entirely geological. Its rings are so even and so eye-catching that many people first imagine an impact or some lost artificial design. But its strange beauty comes from natural uplift and erosion, working slowly over immense spans of time. Pamukkale in southwestern Turkey is famous for bright white terraces built by mineral-rich thermal waters. These terraces look almost like frozen waterfalls, or like steps made of cloud and snow. But they are not icy at all. They are stone formed by water carrying dissolved minerals and laying them down in thin layers again and again. Calcite-laden spring water flowing down a cliff nearly 200 meters high created the site's terraced basins and petrified waterfall forms. That means the landscape was built not by one sudden event, but by repeated flow, cooling, and deposit over long periods. The result is a place where water has slowly made rock look soft, folded, and almost poured. UNESCO describes Pamukkale as an unreal landscape because of its mineral forests, basins, and white deposits. That description fits because the place seems to blur categories. It looks part cliff, part sculpture garden, part frozen water, and part ancient ruin. It is one of those rare places where the earth seems to have imitated art. The white surfaces are not snow or ice, but mineral deposits left behind as hot water cools and loses dissolved carbonates. This is important because the visual effect can fool the eye. What looks soft and cold is actually the record of warm flowing water and chemical change. It is a landscape written by invisible ingredients carried in spring water. Daylol in Ethiopia sits within the Danakil Depression, one of Earth's harshest landscapes. Even among already extreme places, Daylol stands out. The ground there can glow with yellow, green, orange, and white tones, and the whole area can look more like a painting of another planet than a real place people can visit. Daylol's vivid colors come from hot, acidic, salty fluids interacting with mineral-rich evaporite deposits. In simpler terms, Hot water loaded with powerful chemicals moves through salt-rich ground and leaves behind brilliant minerals. Those colors are not decoration. They are evidence of intense chemistry happening right at the surface, where heat, salt, and water meet. Daylol looks unreal because its pools and crusts are shaped by geology, hydrothermal chemistry, and desert climate all at once. That combination matters. Heat brings fluids upward, minerals stain the ground, and fierce dryness helps preserve the strange patterns. The place is not shaped by one simple force, but by several extreme conditions acting together. Blood Falls in Antarctica is a reddish outflow seeping from Taylor Glacier into Lake Bonny. At first glance, it looks almost shocking, because the clean white and blue world of ice is suddenly stained with deep rust-red color. It gives the impression that the glacier itself is bleeding, which is why the sight is so memorable. The feature is famous because it makes a glacier look as if it is bleeding. That visual effect is powerful because it goes against what people expect from Antarctica. Instead of pure whiteness, the eye sees something dark, vivid, and unsettling. It reminds us that even the coldest places can hide strange chemistry and hidden fluids beneath the ice. The place feels otherworldly because it combines ice, desert, hidden water, and a startling red plume in one scene. Antarctica's dry valleys are already unusual because they are so barren and exposed. Add a subglacial outflow of red-stained brine, and the result becomes a place that seems to combine several worlds at once. The Cave of the Crystals in Nica, Mexico, lies about 300 meters below ground. Deep beneath the surface, in dangerous heat, this hidden chamber contains giant crystals so large that they can seem more like pillars or fallen beams than like ordinary crystals. It is one of those places where natural scale exceeds human expectation. Its chamber contains some of the largest natural gypsum crystals ever found. These are not delicate little formations lining a wall. They're massive, luminous structures that fill the cave like the bones of a mineral cathedral. The size alone changes how the mind understands crystal growth, turning something usually thought of as small into something monumental. The largest known crystal there is about 11.4 meters long. A crystal that long is large enough to rival the length of a bus. When the mineral reaches that size naturally, it begins to feel less like an object and more like part of the architecture of the cave itself. Some nacre crystals are estimated to weigh around 12 tons. That enormous weight makes them feel even less like jewels and more like geological giants. They are delicate in structure, yet colossal in mass, which adds to the strange contrast that makes the cave so unforgettable. The cave is dangerously hot, with air temperatures reaching about 58 degrees Celsius and humidity often above 90%. That means this remarkable underground space is not simply beautiful. It is also physically punishing and difficult for humans to endure. The same conditions that helped preserve and grow the crystals also make the cave one of the least welcoming wonders on Earth. Nica is strange because it turns a cave into something resembling a crystal cathedral on a scale that dwarfs people. Most caves impress by darkness, depth, or dripping stone, but this one transforms underground space into a chamber of giant transparent beams. It feels almost as if geology briefly crossed into fantasy. The Great Blue Hole in Belize is a large marine sinkhole near the center of Lighthouse Reef. Seen from above, it appears as a nearly perfect dark blue circle in bright turquoise water. That contrast is part of what makes it so visually powerful. It looks like a hole punched through the reef by some giant tool. Its almost perfectly circular dark center makes it visible even in satellite images as a geometric void in the reef. Nature often produces irregular forms, but this one looks strikingly clean and deliberate. The eye is drawn to it immediately because its dark, round shape stands apart from the lighter water and surrounding coral. Few places on Earth look more like a missing piece punched cleanly through a tropical reef. That impression comes from both its shape and its setting. It is not just a blue depression in the sea. It is a dark, simple circle, surrounded by one of the brightest and most colorful marine environments, which makes the contrast feel almost unreal. Socotra Archipelago lies in the northwest Indian Ocean near the Gulf of Aden and includes 4 islands, plus 2 rocky islets. It is not famous for one single rock, cave, or lake, but for an entire, isolated world of unusual life and landscape. Its remoteness has allowed it to develop a character that feels set apart from nearby regions. Socotra's main island is about 250 kilometers long. That gives the archipelago enough size to contain a surprising range of environments, from coastal zones to mountains and plateaus. It is large enough to feel like a self-contained world, not just a small island with one odd feature. UNESCO highlights Socotra as globally important because of its exceptionally high endemism. Endemism means many of its living things exist nowhere else on Earth. This gives the islands a sense of biological isolation, as though life there followed its own path for a very long time. About 37% of Socotra's 825 plant species occur nowhere else on Earth. That is an extraordinary share of unique plant life in one place. It means that more than a third of the island's plant world belongs only to Socotra, helping explain why its landscapes can look so unfamiliar. About 90% of its reptile species are endemic to the archipelago. In other words, almost all of its reptiles are local originals rather than widespread species found elsewhere. That level of isolation is one reason Socotra feels so biologically unusual. About 95% of its land snail species are also found nowhere else. Even the smaller and quieter life of the islands reflects that same pattern of separation. The strangeness of Socotra is not only visible in its famous trees, but also hidden in countless small creatures that evolved there alone. Socotra is famous for the dragon's blood tree, whose umbrella-like shape makes the island look almost invented. These trees do not just add interest to the landscape, they define it. Their flat-topped crowns give hillsides and plateaus a silhouette that can seem closer to illustration than to ordinary botany. The archipelago sits at a crossroads between the Red Sea and the Indian Ocean, which helps explain its long importance as a natural and cultural outlier. Being at a crossroads often brings exchange, but being an island group also preserves separation. Socotra carries both influences at once, which adds to its distinct identity. Socotra often feels alien to visitors because its strangeness comes from evolution in isolation rather than from a single dramatic geologic event. There is no one explosion, one crater, or one cliff that explains it. Its oddness is layered into the living fabric of the islands themselves. Lençois maranhenses in Brazil is a vast dune field capped by seasonal freshwater lagoons. At first glance, it looks like a desert. Then water appears between the dunes in smooth blue and green pools, and the whole scene becomes difficult to classify. It is one of the clearest examples of a place that looks like one kind of world and behaves like another. UNESCO inscribed Lençois maranhenses as a World Heritage Site in 2024. That recognition reflects how rare the landscape is on a global level. It is not simply a beautiful dune field. It is a large and unusual system where sand, rainfall, and hidden ground conditions create a seasonal pattern unlike that of most dry landscapes. The property covers more than 156,000 hectares. That enormous extent matters because the strangeness of the place is not confined to one small scenic corner. It stretches over a broad area. allowing the repeating pattern of dunes and lagoons to become part of the identity of the entire region. About 90,000 hectares of that area are extensive dunes and lagoons. This means a huge portion of the landscape is defined by the direct meeting of sand and fresh water. That pairing is what makes the place so visually surprising and so easy to remember. Winds shape the sand into long Bafen dunes. These are crescent-like dunes formed by steady wind movement, and they give the land a flowing, wave-like structure. Even without water, the dunes already suggest motion, as though the ground itself were drifting. Some dune systems extend for tens of kilometers along the coast. That long reach helps create the sense that the landscape goes on almost without end. The repetition of pale dunes over such a wide distance makes the lagoons feel even more miraculous when they appear. The lagoons are most impressive after the rainy season, when they reach peak water levels. This seasonal rhythm is central to the place. The landscape changes character depending on the time of year, moving between drier stretches and bright water-filled basins. The fresh water is held in place by impermeable material beneath the sand. Without that hidden layer, the water would simply drain away. So part of the wonder of Lensois Maranhenses comes from what cannot be seen, an underground condition that allows those calm pools to gather and remain. The place is not a true desert because it receives far more rainfall than deserts normally do. This is one of the reasons it feels so surprising. It has the shape and broad appearance of a desert, but not the climate people usually associate with one. Lensois Maranhenses feels impossible because it looks like a desert from above, but behaves partly like a seasonal lagoon system. The mind wants to place it in a single category, but it resists that. It is both dune sea and freshwater landscape, depending on when and how you see it. Salar de Uyuni in Bolivia is the world's largest salt flat. It is one of those places where scale alone becomes part of the mystery. The white surface stretches so far and so evenly that it can feel less like terrain and more like an abstract plane laid over the earth. Its area is about 10,582 square kilometers. That immense size means the salt flat is not merely a local curiosity. It is a continental-scale surface, large enough to alter the sense of distance and to make horizons feel unusually clean and far away. The Salar lies high in the Andes on the Altiplano at roughly 650 meters above sea level. Its height adds another layer to its identity. This is not a sea-level salt pan under blazing tropical sun, but a vast, bright surface set high in a mountainous region. It formed through the transformation and drying of prehistoric lakes. So beneath its still, white surface lies the memory of water. The flat is the remains of ancient lake systems, preserved in mineral form after long climatic and geological change. The salt crust is extremely flat, which is why the site is famous for mirror-like reflections after rain. When a thin layer of water spreads across the surface, sky and ground blend together. The effect can be so complete that the horizon seems to disappear. Across the Salar, elevation variation is less than a meter relative to Earth's curvature. That astonishing flatness is one of the reasons the place feels so unnatural, even though it is entirely natural. Human-made surfaces are often flat. A natural one on this scale feels almost impossible. Because it is so vast, bright and uniform, Salar de Uyuni is used to calibrate Earth-observing satellites. That means the place is not only visually strange, but scientifically useful. Its consistency makes it valuable for measuring and checking instruments looking down from space. It is considered far more effective for some calibration work than the open ocean. That is a remarkable role for a salt flat. An inland mineral landscape becomes a kind of reference surface for observing the planet, which gives it an importance beyond scenery. The Salar also contains important lithium-bearing brines beneath the salt crust. So, under the silent white surface lies chemistry tied to modern technology. The place is ancient in origin but deeply connected to present-day human demand for materials. Salar de Uyuni is strange because it can look either like cracked white ground or like a perfect sky mirror, depending on the season. In dry conditions, it emphasizes texture and vastness. In wet conditions, it seems to erase the boundary between earth and sky. The Chocolate Hills of Bohol are a field of conical limestone hills spread across central Bohol. Their power comes from repetition. One hill would be curious. Hundreds and hundreds of similar hills gathered together create a landscape that feels rhythmic, patterned, and strangely deliberate. Estimates put the number of hills at least 260, and possibly as many as 776. The uncertainty in the count almost adds to their mystery. There are so many that the landscape stops feeling like a collection of separate features and starts feeling like a single textured surface. The hills rise from a relatively flat to rolling landscape rather than from a mountain chain. That makes them stand out more strongly. Instead of blending into a larger line of peaks, they appear as separate rounded forms scattered across gentler terrain. The formations are a karst landscape built in limestone. In other words, water and time shaped soluble rock into these unusual forms. Their softness of outline hides a long history of chemical weathering and erosion. They are called chocolate hills because the grass covering them turns brown in the dry season. This seasonal color shift changes the emotional feel of the landscape. Green hills become brown domes, and the whole region takes on the look of countless chocolate drops spread across the land. The hills are unusual because they are so numerous and so similar in size and shape. Nature often creates variation, but here the repeated rounded pattern is part of what makes the view so memorable. The eye keeps expecting the pattern to end, and it simply continues. Bohol Island Broader Geopark also includes caves and sinkholes, showing that the hills are part of a much larger karst system. So the cones are only the visible expression of deeper geological processes. Beneath and around them lies a wider landscape shaped by water moving through limestone. From a distance, the Chocolate Hills can resemble a field of giant earthen drops frozen in place. That image captures their stillness and their strange regularity. They look almost poured, as if the ground once softened and then hardened mid-motion. White desert proves that a desert can feel surreal, even without bright colors, simply through shape and contrast. In a world of white chalk forms, silence, and open space, ordinary desert expectations fall away. Strange landscapes do not always need strong color. Sometimes pale stone and shadow are enough. Tsingdi de Bemaraha in Madagascar is a karst landscape of razor-sharp limestone pinnacles. Unlike smoother hills or rounded towers, this terrain looks jagged, crowded, and almost dangerous from a distance. It is a reminder that stone shaped by water can become not only beautiful, but severe. The Giant's Causeway in Northern Ireland is made of about 40,000 interlocking basalt columns created by ancient volcanic activity. That number helps explain why the site feels so immense and organized at the same time. These columns were formed when molten rock cooled and hardened, then cracked in repeating patterns. What seems at first like a giant man-made pavement is really the result of heat leaving rock in a very orderly way, with nature producing thousands upon thousands of tightly fitted stone shapes. Most of the Giant's Causeway columns are hexagonal, but some have 4, 5, 7, or 8 sides. This variation is important because it shows that the pattern was not drawn with perfect geometry, but formed naturally as the cooling rock adjusted to pressure and space. A six-sided shape is often the most efficient way for a surface to crack evenly, but nature still allows small differences. That is why the columns look regular enough to amaze the eye, yet irregular enough to prove they were not designed by human hands. The causeway formed roughly 50 to 60 million years ago when lava cooled, contracted, and cracked into columns. The key process here is contraction. When very hot lava begins to cool, it shrinks, and that shrinking creates tension in the solidifying rock. As the tension builds, cracks spread through it in a repeating way. Over time, that cooling and cracking built the remarkable vertical stone columns that survive today, giving us a direct look at an ancient volcanic event frozen in place. The tops of many causeway columns form natural stepping stone surfaces that appear to run into the sea. This happens because the columns are packed closely together and many were broken or worn down to similar heights. The result is a broad rocky surface that looks almost paved. It gives the place its famous sense of order, as though the volcanic process created not only pillars, but also a pathway. The site sits below basalt cliffs on the edge of the Antrim Plateau, rather than as a separate isolated rock field. That larger setting matters because the causeway is not a random patch of strange stones. It is part of a much wider volcanic landscape. The cliffs above and the columns below belong to the same geological story, showing how large lava flows once covered the region before erosion later revealed the patterns we now see. UNESCO recognizes the Giant's Causeway for both its scenery and its importance in understanding Earth's volcanic history. That scientific value comes from how clearly the site shows the relationship between lava flow, cooling, contraction, and rock structure. It is beautiful, but it is also educational. In one place, visitors can see how ancient volcanic material turned into one of the clearest examples of columnar basalt on Earth. Weathering at the site has produced named shapes such as the organ, the giant's boot, and the camel's hump. These forms were not made in the original eruption. They were created later, as wind, rain, waves, and temperature changes slowly wore different parts of the rock at different rates. Over long stretches of time, erosion turned a volcanic formation into a landscape full of recognizable shapes. The Richat structure was once suspected to be an impact crater, but geologic studies show it is an uplifted dome. That means the Earth's crust in that area rose upward rather than being blasted downward by an outside collision. This is important because the structure's circular form seems at first to suggest a violent strike from space, yet its true story comes from internal geologic movement and long-term erosion. In the Richat structure, older rocks are exposed in the center, while younger layers form outer rings. This arrangement helps scientists understand how the dome was lifted and then worn down. When the dome rises, erosion gradually strips away material from the top, revealing deeper and older layers in the middle first. The rings are like pages of geological history, becoming visible from the inside outward. Both igneous and sedimentary rocks are present in the Richat structure. That mixture tells us that the area has experienced more than one kind of geological history. Sedimentary rocks point to older deposited layers, while igneous material shows the role of heat and internal earth processes. Together, they make the formation more complex than a simple ring of one rock type. Faults cut through parts of the Richat structure, showing that its rings are not perfectly untouched circles. Faults are fractures where the rock has shifted, and their presence reminds us that even the most visually neat landforms are shaped by stress and movement. The eye of the Sahara may look smooth and symbolic from above, but up close, it reflects a more broken and dynamic history. Its ballsy appearance comes from erosion revealing onion-like layers of rock. That is a useful image because it helps explain why the rings exist. The structure contains layers arranged around a central uplift, and erosion gradually exposed them one after another. Instead of removing everything evenly, weathering highlighted the differences between those layers, making the circular bands more visible over time. The name Pamukkale means cotton palace. The name fits the appearance because the terraces look soft, white, and piled in thick folds, almost like fabric or cotton seen from far away. But the softness is an illusion. The palace-like look comes from mineral deposits laid down by flowing water, which gradually built the bright stone basins and ledges. Pamukkale is joined historically to Hierapolis, an ancient thermal spa city established in the Hellenistic period. This connection shows that the geology of the place influenced human settlement and culture. People were drawn there by the warm mineral waters, and over time, a city grew beside the terraces. So the strange natural surface and the human-built past are closely linked. The site combines geology and archaeology in the same landscape, rather than separating them into different zones. This makes Pamukkale especially interesting because the terrain itself helped shape how people used the place. The mineral-rich waters created the terraces, and those same waters also supported bathing, settlement, and ritual activity. Nature and history sit together there in a very direct way. Pamukkale's terraces form because water repeatedly spreads, cools, evaporates, and deposits new layers. This is a slow building process rather than a single event. As warm spring water flows over the surface, it carries dissolved minerals. When conditions change, those minerals come out of the water and settle onto the ground. Repeated again and again, that process creates the layered white steps. The effect is striking because the terraces look soft, like draped fabric even though they are stone. This happens because the mineral deposits follow the movement of water, collecting in rounded edges, shallow basins, and smooth curtains. The shapes preserve the memory of flowing liquid, even after the minerals harden into rock. Pamukkale is one of the clearest examples of a place where chemistry creates a landscape that resembles architecture. There is no mason and no blueprint, but the terraces look like staircases, basins, and walls. The chemistry of dissolved carbonates, cooling water, and steady deposition allows simple natural processes to build something that seems intentionally designed. Spotted Lake near Osoyoos in British Columbia develops separate mineral spots as summer evaporation removes much of the water. In cooler or wetter times, the lake surface is more continuous, but heat and dryness change that. As water disappears, separate pools remain in low areas where minerals become more concentrated. That seasonal shrinking creates the spotted pattern for which the lake is known. The lake is rich in minerals, including calcium, magnesium sulfate, sodium sulfate, and others. Those ingredients matter because they shape both the appearance and behavior of the lake. Different minerals dissolve, settle, and crystallize in different ways, which helps explain the lake's varied colors and the formation of its separate circular pools. As evaporation continues, the spots can change size and color through the season. This means the landscape is not static. It responds to heat, water level, and the concentration of dissolved substances. The lake becomes almost like a living chemical map, shifting in appearance as the summer progresses. Each visible spot is effectively a small mineral concentration zone shaped by evaporation. That makes the place scientifically interesting because the lake is not only visually patterned. It is also a system where chemistry becomes visible at the surface. Each spot reflects local conditions in water depth and mineral content. The lake shows how a single, shallow basin can produce a highly patterned surface without any human design. No walls divide the pools, and no color has been added by hand. The arrangement emerges naturally from the shape of the basin, the minerals in the water, and the rhythm of seasonal drying. Lake Natron in Tanzania is a warm, salty, highly alkaline lake that is inhospitable to most life. Its chemistry makes it extreme, and that extreme environment shapes everything about the ecosystem. Many organisms cannot tolerate the salt and alkalinity, which is why the lake seems so hostile when compared with more ordinary bodies of water. Depending on rainfall, Lake Natron's alkalinity can reach about pH 9 to 10.5. That is far above the level of neutral water and helps explain why the lake feels chemically harsh. Rainfall matters because it can temporarily dilute the lake. In drier periods, evaporation concentrates the salts and raises the alkalinity again. Mud temperatures around the lake can reach about 50 degrees Celsius. That heat adds another layer of difficulty for life. It is not only the chemistry that makes the environment extreme, but also the temperature of the shallow, exposed surroundings, especially under strong sun. Despite these harsh conditions, a few specially adapted species live there. This is one of the most interesting parts of extreme environments. Conditions that exclude most organisms can create space for a small number of specialists. Those adapted species are able to use a habitat that many others cannot. Its caustic environment helps protect flamingo nests by discouraging predators. This shows how a difficult setting can become a biological advantage. What is dangerous or uncomfortable for many animals creates a safer breeding environment for lesser flamingos, allowing them to nest with less disturbance. The lake's strangeness comes less from giant landforms than from extreme water chemistry. That is an important distinction. Some places seem weird because of mountains, caves, or towering rock shapes. Lake Natron is different. Much of its uniqueness lies in what is dissolved in the water and how that chemistry controls life and appearance. The Danakil Depression is a rift environment, meaning the crust there is being pulled apart. Rift zones are places where the Earth's surface is under tension, and that tension allows heat and material from below to influence the landscape more directly. This larger tectonic setting helps explain why Daylol is so active and unusual. Daylol lies on the Eta-Ale axial rift segment, which also hosts other active volcanoes. So Daylol is not an isolated oddity. It belongs to a broader system where crustal stretching, volcanism, and geothermal activity all interact. That regional context helps explain why the area contains so many extreme landforms and hot features. The site is unusual because it is often described as a salt volcano rather than a classic cone of ash and lava. That description captures how different Daylol is from the volcano image many people carry in their minds. Instead of a steep mountain of dark rock, it is a low, chemically active area where heat interacts strongly with evaporite deposits. The volcano's summit crater is about 100 meters across. While that is modest in size compared with giant volcanic craters, it still marks a focal point of the system. Its scale fits the nature of Daylol, which is less about towering height and more about concentrated surface chemistry and geothermal activity. Daylol rises only gently above the surrounding salt plain, and in places is still below sea level. This gives the area a peculiar physical character. It does not dominate the land as a dramatic cone. Instead, it feels embedded in the wider salt landscape, as though the strange activity is bubbling out of the plain itself. A phreatic eruption took place there in 1926. A phreatic eruption happens when water is suddenly heated by underground heat and flashes into steam, causing an explosive release. That kind of eruption fits Daylol's nature very well, because the place is strongly shaped by hot fluids and shallow geothermal processes. The Chocolate Hills area ranges roughly from 100 to 500 meters above sea level. These heights are not enormous, yet the hills still create one of the most memorable repetitive landscapes in the world. Their moderate scale helps preserve their rounded forms, and makes them feel approachable rather than overwhelming. The site was declared the Philippines' third National Geological Monument in 1988. This recognition reflects the scientific and visual importance of the hills. They are not only scenic landmarks, but also a valuable example of karst landform development in limestone. Egypt's White Desert lies in the Farafra Depression of the Western Desert. Its location matters because depressions often gather distinctive sedimentary and erosional histories. In this case, the White Desert sits in a broader desert system, where wind has had the time and space to sculpt exposed chalk into remarkable forms. It was established as a protected area in 2002. Protection is especially important in fragile erosional landscapes because the same features that make them beautiful can also make them vulnerable. Once damaged, the slow, natural shaping that created them cannot be quickly restored. The park covers roughly 300 square kilometers. That scale means the strange chalk formations are part of a broader protected setting rather than a tiny isolated patch. The larger area allows dunes, cliffs, wadis and other desert features to interact with the sculpted white outcrops. The White Desert includes not only chalk formations, but also dunes, cliffs, wadis and oasis features. This wider mix shows that the area is not a one-note landscape. Its strangeness comes from the interaction of different desert landforms, with chalk towers standing within a larger system of dry valleys and shifting sands. Wind erosion is the main artist there, gradually carving chalk into freestanding shapes. Unlike landscapes built mostly by flowing rivers or lava, the White Desert owes much of its appearance to moving air carrying sand. Over long periods, that constant abrasion sculpts the soft rock into pillars, caps, and abstract forms. Danshia landscapes form in red sedimentary rocks shaped by uplift, weathering, and erosion. This process begins with layers of sediment being laid down and hardened into rock. Later, tectonic forces raise them, and weathering then cuts into them. Over time, cliffs, ridges, and valleys emerge, giving the landscape its dramatic structure. UNESCO describes China Danxia as featuring red cliffs, pillars, towers, ravines, valleys, and waterfalls. That list shows how varied a single rock system can become when different kinds of erosion work over long periods. Instead of producing one repeated shape, Danxia processes generate a whole family of landforms. Jiangyi's scenic strata are multicolored fluvial lacustrine rock formations from the early Cretaceous. Fluvio-lacustrine means the sediments were laid down in rivers and lakes long ago. That origin is important because it explains the layering. Different environments deposited different materials, which later became the colorful bands seen today. The colorful hills have been folded, which helps expose bands of different rock colors and angles. Folding bends the rock layers instead of leaving them flat. Once erosion cuts into those bent layers, the colors appear as stripes and waves across slopes and ridges, making the geology far easier to see. The site shows how sediment type, oxidation, and tectonic deformation can combine to create a landscape that looks painted. Different sediments produce different colors, oxidation changes mineral tones, and tectonic forces tilt and fold the layers. Erosion then reveals the result, turning geological history into visible patterns on a mountain scale. Shilin Stone Forest is a karst landscape of dense limestone pillars that can rise 20 to 50 meters high. These tall stone forms began as limestone laid down under ancient seas. Much later, uplift brought that rock above water, and rainwater slowly dissolved it along cracks and weaknesses, leaving pillars standing where other material disappeared. UNESCO notes that the Shilin formations are scientifically important for understanding multi-stage karst evolution. That phrase means the landscape did not form in one simple phase. It changed through multiple episodes of uplift, weathering, dissolution, and surface adjustment. Each stage added something to the final stone forest. Parts of the site are more than 270 million years old. That age refers to the deep geological history of the rock itself, which began long before the modern shapes appeared. So the landscape combines very ancient material with much later sculpting processes. The area was once covered by an ancient sea before uplift and dissolution shaped the current landscape. This is a key part of the story. The rock began as marine deposits, then tectonic movement lifted it, and finally water slowly carved it. Sea, uplift, and rain all played a role in building the stone forest. The pillars owe their shape to limestone weathering and dissolution, not to volcanic cooling. That distinction matters because tall stone columns can have different origins. At Shilin, the pillars are not frozen lava structures. They are the leftovers of soluble rock gradually removed around them by water. The caves limestone at Waitomo formed when the region was under the sea, about 30 million years ago. This means the cave system began not as empty chambers, but as marine sediment full of tiny remains from sea life. Over long periods, that sediment hardened into limestone, which was later lifted above sea level. Fossilized marine remains such as shells and corals helped create the limestone of the Waitomo region. So even before the cave took shape, the building material had a biological origin. Ancient sea creatures contributed to the rock that later became the glowing underground world known today. Glowworm larvae hang sticky threads that trap prey attracted by their blue-green light. This behavior is both delicate and effective. The larvae use light to draw in insects, then capture them with suspended threads. It is one of the reasons Waitomo feels so unusual, because its famous appearance comes from animal behavior inside a cave system shaped by geology. The cave includes a chamber known as the cathedral because of its large size and notable acoustics. Sound behaves differently in large enclosed spaces, and in this chamber, the shape and volume of the cave allow voices and music to carry in a rich, lingering way. That means the cave is not only visually unusual, but also acoustically unusual. The rock walls, open interior and enclosed air together, create a space where sound seems to float and echo in a calm, powerful way. The underground stream is crossed by boat in near darkness, so the glowworms appear like a living starfield. This darkness matters because the effect depends on contrast. When the cave is dim and quiet, the tiny blue-green lights stand out against the ceiling, like distant stars against a night sky. The glowing points are not reflections or minerals. They are living lava using light as part of their survival strategy, which makes the site even more remarkable. Waitomo is strange because its spectacle comes from insects behaving like a night sky inside rock. Most famous caves are admired for stone, water, and shape. Waitomo adds biology into that underground world in a very direct way. The glow does not come from crystals or lighting effects built by nature in stone, but from small organisms making light in darkness, turning the cave ceiling into something that feels almost cosmic. Blood Falls occurs in the MC Murdo dry valleys, one of Antarctica's most unusual ice-free desert regions. That setting is important because it places the feature in a landscape already full of contradiction. Antarctica is often imagined as endless ice, yet the dry valleys are barren, rocky, and desert-like. Blood Falls appears within that already unexpected environment, making it feel even stranger than it would in a more typical glacier setting. NASA notes that the red stain is visible even in satellite imagery. This tells us that the color is not just a small local detail seen only up close. It is strong enough and extensive enough to stand out from above, even against a vast icy region. When a feature is visible from space, it usually means the process behind it is not only unusual, but also large enough to leave a clear mark on the landscape. The outflow emerges from beneath the glacier, rather than from a rock face beside it. That detail matters because it points to hidden activity below the ice. The glacier is not simply melting at the surface and letting colored water run down. Instead, the source lies underneath, where trapped brines and buried systems have remained separated from the open air until they find a way out. The visual shock of blood falls comes from a liquid-looking stain appearing in a place people expect to be only white and blue. Human expectation plays a big role in why the feature is so memorable. In icy landscapes, people expect pale tones, clear meltwater, and clean snow. A dark red flow breaks that pattern immediately, which is why the site has such strong emotional and visual impact. The site is tied to unusual subglacial brines rather than simple surface meltwater. Brines are very salty waters, and their chemistry can stay liquid in conditions where ordinary fresh water would freeze. That helps explain why blood falls can exist in such a cold place. The feature depends on hidden salty water, not just ordinary thawing at the surface. Blood falls is one of the clearest examples of Antarctica producing colors associated more with rust or wounds than with ice. This color difference matters because it changes how people emotionally read the landscape. Instead of purity and cold brightness, the eye sees something earthy, metallic, and almost biological. The result is a feature that feels dramatically out of place, even though it is entirely natural. The giant crystals at Naka formed extremely slowly over at least hundreds of thousands of years. Slow growth is a major reason they became so enormous. When conditions remain stable for extremely long periods, crystals can continue adding material in an orderly way without being broken or disrupted. Their huge size is a sign of patience in nature, where time can do what no sudden event can accomplish. The chemistry involved anhydrite dissolving and gypsum crystallizing as temperatures changed. That process may sound technical, but the basic idea is simple. Underground heat and water created the right conditions for one mineral state to give way to another. As those conditions shifted, gypsum was able to grow in large, clear forms. The crystals are therefore the result of very specific temperature and water chemistry working together over long periods. The cave was discovered in 2000 during mining operations. This detail is fascinating because it shows how easily even extraordinary places can remain hidden underground until human activity accidentally opens a path to them. The cave was not found because people expected a crystal chamber there. It appeared because mining exposed a concealed part of the earth that had been sealed away. Once pumping stopped, the cave system reflooded, making ordinary access impossible again. That means the cave briefly entered human awareness and then largely returned to protected isolation. The same underground water conditions that helped create the crystals also make the chamber difficult to keep open. In a way, the cave revealed itself for a short time and then withdrew again. The Great Blue Hole was once a dry cave system formed when sea level was lower during glacial periods. This fact changes how we understand the feature. Today it looks like a marine sinkhole, but in the past it was part of a land-based cave environment. That means the hole belongs to two different worlds in Earth's history. First dry and exposed, later drowned and submerged. Stalactites inside the blue hole show that the cave formed during several different low-level episodes. Stalactites grow in air-filled caves where water drips from ceilings, so their presence proves the cave was once above sea level. Because there are signs of multiple phases, the cave's history is not linked to a single moment. It reflects repeated changes in climate and sea level over very long spans of time. Rising seas eventually flooded the cave and turned it into a submerged sinkhole. This is a good example of how climate-driven sea level change can completely transform a landscape. A place that once had air-filled chambers and hanging formations became part of a reef and marine system. The blue hole is therefore a record of environmental change written into the shape of the Earth. The Blue Hole Natural Monument is one of the 7 protected areas in the Belize Barrier Reef Reserve System. Protection matters because the site is not only visually famous, but also part of a much larger ecological and geological network. The Blue Hole exists within a reef system that supports marine life and preserves the broader environmental setting around the sinkhole. The fairy chimneys in Cappadocia exist because softer material eroded away faster than capped portions above them. This is a beautiful example of uneven erosion. When a harder piece of rock protects the softer rock below it, the surrounding material disappears first. Over time, that leaves behind pillar-like forms with caps, almost like natural stone mushrooms or towers. The soft volcanic landscape of Cappadocia was built from eruptions linked to major nearby volcanoes such as Isis and Hassan. This volcanic origin matters because it explains why the rock is so easy to carve and so vulnerable to shaping by erosion. Ash, tuff, and other volcanic materials settled over the landscape long ago, creating the raw material that wind, water, and human hands later transformed. Erosion continues to create new fairy chimneys and rock pillars in the region. That means Cappadocia is not a finished landscape. It is still changing, slowly but steadily. Some forms are growing clearer as surrounding material wears away, while others may weaken and collapse over time. The strange scenery people admire today is part of an ongoing process, not a permanent final state. Mass tourism and natural erosion both threaten the site, showing that even unusual rock forms are temporary on geologic timescales. This is an important reminder that beauty in nature can be fragile. The same softness that allowed the rock to be shaped into remarkable forms also makes it vulnerable to damage from footsteps, weather, and time. The landscape can feel like an inhabited stone hive because openings, rooms, and towers blend together. This impression comes from the close relationship between natural erosion and human carving. Rock forms that already looked like towers or chimneys were opened up into dwellings, chapels, and passageways, making the land seem partly natural and partly architectural at the same time. Mono Lake's famous tufa towers form where freshwater springs meet alkaline lake water and precipitate calcium carbonate. The key process here is chemical contrast. Fresh water rising from below carries ingredients that react differently when they meet the highly alkaline lake. As a result, calcium carbonate is deposited and builds up around spring openings, forming those unusual towers. The tufa towers provide habitat as well as scenery, including nesting or perch sites for birds and habitat for alkali flies. This makes the towers more than just visual landmarks. They become part of the local ecosystem. Their shapes create shelter, structure, and useful surfaces in a lake environment that might otherwise seem chemically harsh and simple. Mono Lake supports trillions of brine shrimp and alkali flies. That number is so large because the lake's chemistry excludes many predators while still supporting these specially adapted organisms. Their abundance then helps support the larger food web, especially birds. So what seems at first like a lifeless saline lake is actually a place of intense biological productivity. It is an important stopover and feeding area for 1 to 2 million birds each year. That role depends on timing, migration, and food availability. Migrating birds need reliable places where they can rest and refuel, and Mono Lake provides vast quantities of food in the form of flies and shrimp. Its strange chemistry therefore supports a very large seasonal movement of life. More than 300 resident and migrant bird species occur in the surrounding Mono Lake ecosystems. This diversity shows that the lake's importance extends beyond the water itself. The nearby shorelines, wetlands, and connected habitats all contribute to a larger ecological system where many kinds of birds can survive, feed, or pause during migration. Goblin Valley's goblins are formed where harder caprock protects softer sandstone beneath. Again, the idea is selective erosion. The harder top layers act like shields, slowing the wearing away of the softer rock under them. Over time, this produces thousands of separate hoodoo-like shapes that stand as little rock figures across the valley floor. The main concentration of hoodoos covers about 3 square miles. That wide spread is part of what gives the place its personality. It is not one isolated outcrop or one cluster of stone forms. It is a whole field of them, dense enough to create the feeling that the valley is crowded with stone figures. Goblin Valley and Bryce Canyon contain some of the largest concentrations of hoodoos in the world. This comparison helps place Goblin Valley in a global context. Hoodoos are not unique to Utah, but the density and visual impact of these formations there make the site one of the clearest and most striking examples of how repeated erosion can produce a whole landscape of pillars. Unlike a canyon or cliff face, Goblin Valley lets visitors move among isolated rock figures at ground level. That changes the experience. In many dramatic landscapes, the viewer mostly looks from above or from a distance. In Goblin Valley, people can walk between the formations and experience the shapes at close range, which makes the place feel more immersive and almost populated. Its strangeness comes from repetition, with the same basic rock process producing a whole valley of individual shapes. One hoodoo may seem playful, but hundreds of them together create a stronger effect. The mind starts noticing variety within repetition, seeing each figure as similar in origin but slightly different in detail. Goblin Valley shows how erosion can generate a landscape that feels more populated than empty. The valley is made only of rock, shadow, and open desert space, yet the forms suggest bodies, heads, and gestures. The result is a landscape where geology creates the illusion of company. Bisti/Donozing Wilderness covers about 45,000 acres. That broad scale matters because it means the weirdness of the landscape is not confined to one famous formation. The wilderness contains a wide spread of badland terrain where different rock layers, erosion styles, and fossil-bearing zones all contribute to its unusual appearance. The rocks there date mainly to the late Cretaceous. This places them in a time when dinosaurs still lived and inland seas influenced large parts of North America. Knowing that age helps explain why fossils occur there and why the sediments reflect ancient environments very different from the dry badlands seen today. The area protects petrified wood and vertebrate fossils as well as unusual landforms. This combination makes the wilderness especially rich scientifically. It preserves not only scenic geology, but also biological evidence from ancient ecosystems. The place is therefore both a landscape museum and a fossil archive. BLM describes hiking there as travel across unmarked routes through rugged badlands. That ruggedness is part of the experience and also part of the wilderness's character. Without marked trails everywhere, the land feels open, raw, and less controlled, which fits the strange and remote atmosphere of the terrain. The badlands formed from sediments associated with an ancient inland sea. That origin reminds us that dry Hyades landscapes can preserve the memory of vanished waters. Sediments laid down long ago in wetter environments later hardened, lifted, and eroded into the fragile-looking shapes seen today. Bisti is strange because many of its rock forms look fragile and temporary, even though they were shaped over immense spans of time. This contrast is one of the most beautiful things about erosional landscapes. The forms can seem delicate, like they might collapse tomorrow, yet their creation required ages of slow change. It is one of the few famous weird landscapes where fossils and bizarre erosional forms are major attractions in the same terrain. That overlap makes Bisti especially layered as a place. It is not only a site of visual oddity, but also a place where the deeper biological past is physically present in the ground. Tsingy de Bemaraha is described by UNESCO as a forest of limestone needles. The word forest is useful here because the formations stand in dense numbers, creating a vertical landscape with the crowded feel of tree trunks. But unlike a true forest, these trees are sharp stone blades produced by karst dissolution. The reserve also includes the canyon of the Manambalo River, plus forests, lakes, and mangroves. This shows that Tsingy is not just a field of spikes. It is part of a larger protected system, where sharp limestone terrain coexists with water systems and living habitats, adding richness to the region's ecology. The Bemaraha Plateau extends roughly 250 kilometers and is composed of Jurassic limestone. That long stretch of limestone provides the raw material for the Tsingy formations. Over a very large area, the same soluble rock has been carved into one of the world's most severe-looking karst landscapes. The Tsingy formations are not rounded karst towers, but sharp-edged blades and spikes. This difference matters because karst can take many forms. In some places it becomes smooth hills or broad towers. Here it becomes narrow, jagged and knife-like, which gives the landscape its especially dramatic and intimidating appearance. This geology creates a place where moving across the terrain can be physically difficult because of the rock's knife-like nature. The form of the ground affects how animals and people can use the space. In Tsingy, geology is not just something to look at. It is something that shapes movement, access, and even survival. The surrounding habitats support rare and endangered lemurs and birds. That biological detail shows that even an intimidating landscape can become a refuge. Difficult terrain often reduces human pressure and creates isolated niches, allowing unique species to persist. Among karst terrains, Tsingy is distinctive for the extreme sharpness of its relief. In simple terms, the difference in height and angle across short distances is especially intense. That is one reason the place looks so dramatic. The limestone is not merely rough. It rises and cuts into space in a very sharp and crowded way. Many Maaraki boulders have septarian cracks filled with minerals, which gives them a broken turtle shell appearance. Septarian cracks form when the growing concretion develops internal fractures that are later filled by other minerals. This produces both structure and pattern, turning the boulders into geological objects that look almost decorated from within. The boulders were eroded out of surrounding mudstone cliffs by coastal processes. In other words, the ocean and shoreline weathering gradually exposed them from the rock in which they had formed. They were not dropped onto the beach. They emerged from older cliffs as the softer surrounding material wore away. Some remain partly embedded in the cliffs, while others lie free on the beach. This is useful because it lets people see different stages of exposure. Some boulders are still in the process of being revealed, while others have already been separated and rounded out by erosion. Maaraki shows that coastal erosion can reveal geology in forms that seem almost too perfect to be real. Round shapes of that size are rare enough to look artificial, but they are natural concretions shaped by growth inside sediment and later exposure at the coast. The perfection is not manufactured. It is geological. Floodwater in Antelope Canyon carries sand through the narrow passageways, polishing the walls into flowing curves. This is a powerful example of abrasion. Sand in moving water acts like a natural grinding tool, smoothing and sculpting the rock surfaces. Over many flood events, the canyon walls become rounded and wave-like rather than jagged. Upper and Lower Antelope Canyon differ in shape, access, and lighting conditions. That means the famous canyon is not one single experience. Different sections create different visual effects depending on how narrow they are, how light enters them, and how people move through them. Upper Antelope Canyon is widely known for beams of light when conditions are right. These beams appear when sunlight enters through openings above and becomes visible through dust and reflected light inside the narrow chamber. The effect is temporary and depends on both angle and atmosphere, which is part of why it feels so magical. The canyon is visited only through guided tours, because flash floods can be deadly. This rule is not just about organization. It reflects the real danger of a landscape shaped by sudden water movement. A beautiful canyon of smooth curves was built by powerful floods, and those same floods remain a threat. A fatal flash flood in 1997 in Lower Antelope Canyon is a grim reminder of how quickly the canyon can change. That history matters because it keeps the place from being reduced to beauty alone. The same processes that carved the canyon are still active, and they can turn the narrow passageways from calm to deadly in a short time. It is one of the clearest cases where short, violent floods create some of the world's smoothest rock forms. This contrast is central to Antelope Canyon's identity. Sudden force creates lasting softness of shape. A violent process leaves behind elegance. Because Salar de Uyuni is so vast, bright, and uniform, it is used to calibrate Earth-observing satellites. Scientists need large, stable surfaces with known reflective properties to test and adjust instruments. Salar de Uyuni offers exactly that. Its size and flatness make it an unusually reliable natural reference target. It is considered far more effective for some calibration work than the open ocean. Oceans change constantly with waves, clouds, and moving conditions, while the Salar can offer a more consistent reflective surface. That gives this strange salt landscape a role in modern science far beyond tourism or scenery. Salar de Uyuni also contains important lithium-bearing brines beneath the salt crust. This means that under the flat white surface lies mineral-rich liquid with major economic importance in the modern world. Lithium is used in rechargeable batteries and other technologies, so the Salar is not only a visual wonder, but also a place connected to industry and global energy systems. That gives it a second identity, one part ancient geological remnant and one part modern strategic resource. Reed Flute Cave in Guilin, China, is a water-eroded limestone cave known for dense speleothem formations. Speleothems are the cave features built by mineral-rich dripping water, including stalactites, stalagmites, columns, and other stone shapes. The cave formed as water slowly dissolved limestone and created chambers, while later dripping water built decorations inside those spaces. So the cave is both carved out and filled in by water, but in different ways and over different times. The cave is about 240 meters deep and around 500 meters long. Those dimensions help explain why the cave feels like a full underground world rather than a small opening in rock. A cave of that size allows many chambers, passageways, and formation zones to develop. It becomes large enough for people to move through changing spaces, where the atmosphere shifts from one section to another. It gets its name from the reeds outside that can be made into flutes. This is a small but lovely detail, because it connects the cave to its surface surroundings. The name does not come from a mineral feature hidden underground, but from plant life nearby that people noticed and used. That gives the place a natural and cultural identity at the same time. Reed Flute Cave contains stalactites, stalagmites, stone pillars, and stone curtains. These forms all come from mineral-rich water, moving, dripping, and depositing material over time. Stalactites hang from ceilings, stalagmites rise from floors, and when the two meet, pillars can form. Stone curtains appear when water flows along sloped surfaces and leaves minerals in thin, hanging sheets. Together, they give the cave an almost decorative richness. The cave is sometimes called the Palace of Natural Art. That nickname works because the formations can look sculptural and arranged, even though they are entirely natural. Water, gravity, and dissolved minerals have produced shapes that remind people of carved halls, ornaments, and drapery. The phrase suggests beauty, but it also hints at how astonishingly intricate cave-building processes can be. More than 70 ink inscriptions survive inside, with the oldest dating to the Tang dynasty in 792 AD. These inscriptions show that the cave has been known, visited, and remembered by people for a very long time. They add a historical layer to the geological one. The cave is not only ancient in formation, but also part of centuries of human attention and cultural memory. Many formations have been given imaginative names based on what they resemble. This is common in caves because the human mind naturally searches for familiar shapes in stone. A cluster of formations may look like animals, towers, people, or curtains. Naming them does not change the geology, but it helps people connect emotionally to what they see underground. The cave was rediscovered in the 1940 by people fleeing Japanese troops. That gives the site a very specific moment in human history when it again became important. A geological space formed over immense time suddenly became a temporary place of refuge during war. The contrast between ancient cave time and urgent human time makes this detail especially striking. Modern colored lighting has become part of its famous visual style, even though the cave itself is natural. This means the way many people experience the cave today is partly shaped by human presentation. The rock, chambers, and mineral forms are natural, but the colors often seen in photographs are enhanced by lighting design rather than by the cave alone. Reed Flute Cave is strange because it combines deep geological time with centuries of human inscription and storytelling. It is not strange in just one way. The cave is a place where stone took shape over vast ages, while people later added names, memories, writing, and meaning. That combination of natural form and human interpretation gives it a layered and lasting appeal. Dedvlei in Namibia is a white clay pan, famous for its dark, dead camel thorn trees. The visual power of the place comes from this stark contrast. The ground is pale and bright, the trees are dark and skeletal, and the dunes around them glow orange-red. Few landscapes rely so strongly on simple contrast of color and shape to create such a haunting effect. The pan formed when the Tzochab River once flooded the area and allowed trees to grow. This means the place was not always dry and lifeless. At one time, water reached the basin often enough to support trees. That earlier phase is essential to understanding Dedvlei, because the dead trunks seen today are the preserved remains of a wetter ecological past. Later, climate change and dune movement blocked the river from reaching the pan. Once the water supply was cut off, the system changed completely. Sand dunes shifted, and the river no longer fed the area. So the trees were stranded in an environment that could no longer support them. The landscape we see today is the result of that environmental separation. The trees died after losing their water supply. This is a simple fact, but it carries the whole story of transition in the place. The trees did not die from fire or sudden destruction. They died because a hydrological link was broken. A living landscape quietly became a dry one. They did not rot away because the climate is so dry. In more humid places, dead wood would decay with time, helped by fungi, insects, and moisture. But Dedvlei is dry enough that decomposition slows dramatically. As a result, the dead trees remain standing as preserved shapes, almost like charcoal drawings against the bright pan. Estimates put the dead trees at roughly 600 to 900 years old. This age adds to the strange feeling of the site. The trunks are not recent remains. They have stood dead for centuries, preserved by dryness. That means the place is not only visually dramatic, but also a record of long-lasting environmental stillness. Some small plants still survive there by using moisture from fog and rare rainfall. This detail is important because it reminds us that even extremely dry places are not entirely lifeless. Survival may depend on very small inputs of moisture, but some species can make use of them. That makes the landscape harsher looking than it truly is. Deadvale sits among some of the world's highest dunes, including the famous Big Daddy Dune nearby. These towering dunes shape the wider setting and help explain how the river was blocked. They are not just scenic background. They are active participants in the landscape's story, influencing wind, sand movement, and access to water. The place is strange because black skeletal trees stand on a bright white floor beneath orange dunes. This combination is so visually clean and symbolic that the landscape can seem almost staged. Yet each color comes from a different natural source: dark, preserved wood, pale clay, and iron-rich sand catching the light. Deadvale feels less like a forest remnant and more like a preserved silhouette of one. The trees are still there, but only as outlines of former life. They no longer create shade, leaves, or movement. What remains is a memory in wood, standing quietly in a basin where time seems to have slowed. Fly Geyser in Nevada is a small geothermal geyser created accidentally through drilling. This origin makes it especially unusual because the initial opening was human-made, but the feature that developed afterward became a real natural process. It is an example of nature taking over a mistake and turning it into something vivid and complex. A prior well-drilling attempt in 1917 created an earlier feature near the current geyser. This shows that the area's geothermal activity had already begun reacting to human intervention long before the modern geyser became famous. The underground heat and water were present, waiting for a pathway to the surface. The present Pisa began releasing water in 1964. From that point onward, mineral-rich hot water continually built up the feature we now recognize. What started as an accidental opening did not remain a plain hole. Over time, minerals accumulated and biological communities developed, gradually creating a striking mound. Fly Geyser constantly releases hot water rather than erupting only at intervals. This steady release distinguishes it from the better-known image of geysers that build pressure and then burst dramatically. Fly Geyser behaves more like a continuously active geothermal spring structure, slowly building and reshaping itself through ongoing flow. The mound is colored green and red by thermophilic organisms living in the hot, wet environment. Thermophilic means heat-loving. These microorganisms thrive in warm conditions that would be difficult or impossible for many other forms of life. Their presence turns the geyser into not just a mineral structure, but also a living surface shaped by biology. Water from the geyser has built up travertine terraces over time. Travertine forms when mineral-rich water loses carbon dioxide and deposits calcium carbonate. With steady flow, those deposits gradually accumulate into terraces, ridges, and mounded forms. This is how flowing water builds rock instead of simply wearing it away. The surrounding feature includes dozens of pools across a broad area. This matters because Fly Geyser is not just one cone with one stream. It is part of a wider geothermal zone where hot water emerges and spreads, creating a landscape of pools, channels, and colorful deposits. Fly Geyser sits on private land at Fly Ranch rather than in a conventional public park. That detail affects how people encounter the site. It is not a typical open-access natural attraction. Its unusual origin and location make it feel a little more hidden and less formal than many famous geological landmarks. The geyser looks artificial, even though natural mineral deposition is what gives it its shape today. That mixed impression is central to its identity. Human action opened the system, but the colorful mound itself was built by natural processes, by heat, water, minerals, and microbes, working continuously over time. It is strange because a human mistake opened a vent that nature then turned into a vivid geothermal sculpture. That combination of accident and natural creativity makes Fly Geyser stand apart. It is neither fully artificial nor fully untouched. It is a reminder that human action can sometimes create conditions that geology and biology then transform in surprising ways. Lake Hillier in Western Australia is a saline lake on Middle Island in the Recherche archipelago. Its setting contributes strongly to its appeal. The lake sits close to the sea, yet separated from it by land, and occupies a contained basin within an island environment. That isolation helps give it a distinct character. The lake is about 600 meters long and roughly 250 meters wide. It is not enormous, and that smaller scale may actually strengthen the visual effect. Because it is compact, the unusual color appears concentrated, almost like a bold patch laid carefully into the island landscape. A narrow strip of land separates the lake from the ocean. This is one of the most striking geographic details about it. On one side there is the open sea, and on the other there is a lake famous for its unusual color. The closeness of those contrasting water bodies makes the scene especially memorable. Lake Hillier became famous for its bright pink color. That fame rests almost entirely on visual impact. Pink is not a color people expect from a lake, especially when the surrounding ocean is blue and the nearby vegetation is green. The unexpected color is what makes the place feel so improbable. Scientists have linked its color to salt-loving microorganisms, including Dunaliella salina and other halophiles. These organisms can produce pigments under the right conditions, and in a highly saline lake, their combined activity can shift the water's appearance dramatically. This is a case where microbiology is visible at the scale of a whole landscape. The pink color was once notable for persisting even when water was taken out in a container. That detail is interesting because it suggests the color came from material within the water itself, not simply from reflections or viewing conditions. The unusual look was part of the water, not just part of the scene. Western Australia's tourism site notes that the lake is no longer as bubble pink as it once was, and that natural conditions may change it again. This is a good reminder that many strange places are not fixed forever in one appearance. Their colors and patterns depend on changing biological and chemical conditions. The lake lies within a protected nature reserve setting. Protection matters because isolated systems like this can be ecologically sensitive. The same unusual conditions that make the lake famous can also make it vulnerable to disturbance. Matthew Flinders recorded the Pink Lake in 1802 after climbing the island's highest point. That historical observation shows that the lake's unusual appearance has attracted attention for a long time. It was striking enough to be noted early in European exploration of the region. Lake Hillier is strange because it looks like a synthetic color sample placed between forest and sea. Yet the color is biological and chemical, not artificial. That contrast between appearance and cause is part of what makes the lake so memorable. Bad Abi Sert in northern Iran consists of stepped travertine terraces formed by mineral springs. Like other terrace-forming hot spring landscapes, it was built slowly by water depositing minerals over time. The result is a layered surface of basins and ledges that looks almost handcrafted, even though it comes from chemistry and flow. The site lies at about 840 meters above sea level. Its elevation gives it a mountain setting quite different from some other mineral terrace systems. That highland context changes the visual experience, placing the pools and steps within a broader upland landscape. Two distinct springs feed the terraces, and their waters have different characteristics. This is important because it means the site is not shaped by one simple source. Different waters bring different minerals and effects, which helps create variation in color, taste, and deposit. One spring is very salty and collects in a small natural pool. High salinity affects not only the water chemistry but also the way deposits form and the kinds of life that may tolerate the environment. It creates one specific part of the site's character. The other spring is sour-tasting and orange because of iron-rich sediments. The orange tone adds strong visual contrast to the terraces, and the iron helps explain why this landscape differs so much in color from more uniformly white terrace systems. The terraces formed as carbon dioxide escaped from mineral-rich water and carbonate minerals were deposited. This process is a basic but powerful piece of natural chemistry. As gases leave the water, dissolved minerals become less stable and settle out, gradually building rock from flowing water. The travertine accumulated over thousands of years into staircase-like pools. That long time scale matters because it reminds us that even delicate-looking mineral structures can represent vast amounts of repeated deposit. Each small layer contributes to the larger form. The site's colors can include orange, red, and yellow. Those warm tones make Badabi Cert visually distinctive among terrace landscapes. Instead of looking icy or chalk-white, it can appear glowing, earthy, and almost fire-tinted. Badabi Cert is often compared to Pamukkale, but its coloration and mountain setting give it a very different visual character. Comparison can be helpful, but it also shows how two places built by related processes can still feel completely different because of local chemistry, landscape setting, and color. It is strange because hot spring chemistry has produced terraces that look both natural and deliberately landscaped. The pools seem arranged, stepped, and composed, yet no planner made them. Water and minerals alone created that careful-looking order. At Spotted Lake, the visible pools can appear blue, green, or yellow, depending on their mineral makeup. These colors are not painted onto the lake, and they are not tricks of the eye. They come from the chemical content of the water in different parts of the basin. As minerals become more concentrated, separate pools take on slightly different visual identities, so the lake can look like a natural surface made of many small colored windows. The lake's odd appearance is caused more by chemistry and climate than by unusual landforms. In many strange places, the shape of the ground is the main reason they look unusual. Here, the basin itself is fairly simple. What makes the lake memorable is what happens to the water as seasons change, as heat removes moisture, and as dissolved minerals become more visible. In wet periods, the surface looks more continuous, but in hot months, it breaks into a pattern of separate rounded basins. This means the lake has a changing visual rhythm through the year. Water level controls whether the surface seems unified or divided. During dry periods, the retreating water leaves behind a more complex patchwork, making the lake seem almost transformed from one season to another. The place is strange, partly because it looks less like a lake than like a giant painter's palette. That comparison feels natural because the eye does not immediately read it as open water. Instead, it sees separated circles, shifting colors, and strong contrast between one patch and another. It is a good example of a place where chemistry changes not only the details, but the whole visual category the mind wants to place it in. Its appearance is seasonal, so the lake does not look equally spotted all year long. This is important because it reminds us that strange landscapes are often dynamic rather than permanent in one form. The famous version of Spotted Lake depends on the time of year, the heat, and the amount of evaporation. Its strangeness rises and falls with the season. Lake Natron is crucial because it is the only breeding location for lesser flamingos. That makes the lake far more than an unusual alkaline basin. It is a key biological stronghold for a major bird species. A place that may seem empty or harsh at first glance turns out to be essential for a very specific and important stage of life. The lake's colors can look dramatic from above because shallow water, salt, and algae create strong tonal contrasts. These contrasts help explain why aerial photographs of natron are so striking. Different depths, mineral conditions, and biological activity can produce patches of red, pink, orange, and pale tones. Seen from above, the lake becomes almost map-like in color. Natron is a reminder that places that seem hostile can still be biologically essential. Humans often assume that harsh environments are empty or unimportant, but that is not always true. In natron's case, the very conditions that make life difficult for many organisms create a protected breeding refuge for flamingos. Lake Natron is one of those rare places where a setting deadly to many animals becomes a refuge for another. This reversal is one of the most interesting patterns in extreme ecology. The lake's chemistry and heat discourage many predators and competitors, but for species adapted to it, those same conditions provide safety and opportunity. At day lull, surface features can appear yellow, green, orange, and white because of iron, chlorine, sulfates, and evaporation. These colors are the visible result of chemistry happening right at the surface. Minerals stain crusts and pools, while intense dryness helps preserve and sharpen those tones. The ground becomes a display of reactions that in many places would stay hidden underground or dissolve away. The Chocolate Hills are called that because the grass covering them turns brown in the dry season. During wetter times, the hills may look greener and more ordinary, but when the dry season arrives, their color shifts, and the whole landscape takes on the appearance that gave it its name. That seasonal change shows how climate can alter not just vegetation, but the identity of a place. From a distance, the Chocolate Hills can resemble a field of giant earthen drops frozen in place. That image captures both their smooth shape and their repeated arrangement. They do not look like a broken mountain range or a normal set of scattered hills. They look as if the land itself briefly flowed and then held still. In Egypt's White Desert, chalk outcrops often resemble mushrooms, towers, and abstract sculptures. These forms come from wind and sand slowly wearing away soft rock, but the results can look surprisingly deliberate. Some shapes seem balanced, some seem carved, and others seem almost playful. It is a landscape where erosion becomes an artist of form. The region's stark whiteness is so strong that moonlight can make the landscape look almost luminous. White surfaces reflect available light very effectively, and in a dark desert setting that can make the formations appear to glow softly at night. This gives the White Desert a very different atmosphere from darker rocky deserts. The place is strange because it replaces the common image of a yellow desert with one that can look icy. Deserts are often imagined in browns, reds, and golds. Here, pale chalk changes that expectation completely. The visual language of the landscape feels more like frost or snow than sun-baked stone, even though it is a hot, arid region. Zhangai's colorful hills are part of the broader China Danxia landscape, recognized by UNESCO. This means the site belongs to a larger category of important redbed landscapes shaped by long-term geological processes. Zhangai is one especially famous expression of that broader phenomenon, where rock layering and erosion together produce extraordinary scenery. UNESCO describes China Danxia as featuring red cliffs, pillars, towers, ravines, valleys, and waterfalls. That wide range of forms shows that Dangxia is not a single shape, but a full landscape style. The same underlying rock history can produce steep walls, isolated structures, deep cuts, and flowing water features, depending on local conditions and erosion. Shanghai UNESCO Global Geopark is known internationally because its hills display color in broad natural stripes rather than isolated patches. The scale of those stripes is part of what makes the place special. Instead of one bright mineral stain here and there, entire hillsides reveal layered color, letting geological history appear like bands on a giant canvas. Its reds and other tones are locked in rock layers, not added by vegetation. This matters because it means the color is part of the structure of the land itself. Plants may come and go with season and climate, but these tones belong to the rock and remain visible as long as erosion continues to expose them. It is one of the clearest places on Earth where sedimentary history becomes visible almost like a topographic rainbow. The layered rock records different periods of deposition, and later uplift and erosion turn that record into something the eye can read directly. In that sense, Zhangyi is both a beautiful place and a visible archive of ancient conditions. The name Stone Forest is literal because the limestone pinnacles resemble a forest from a distance. The comparison works because the pillars stand densely and vertically, much like trunks in a wooded area. But as you get closer, the illusion changes, and you realize the forest is made entirely of weathered rock. The stone forest is not a single grove of rocks, but a broad scenic area with several zones. That wider scale is important because it means the landscape includes variation within the overall pattern. Different sections may contain different densities, shapes, and arrangements of pinnacles, making the place more complex than one simple cluster. Some parts of Shilin look like petrified trunks, while others resemble blades or walls. This variation comes from differences in rock structure, water pathways, and weathering over time. Not every pillar erodes in the same way, so the landscape offers a range of forms within the same limestone system. Shilin is unusual because it creates the illusion of vertical growth from stone, in the same way a normal forest does with wood. The eye reads repeated vertical forms as a forest-like pattern, even when the material is completely different. That is why the place feels at once familiar and deeply strange. Its mixture of geologic age, sharp form, and maze-like structure makes it feel more architectural than natural at first glance. Narrow passages, tall stone elements, and repeating vertical shapes can create the impression of ruined walls, corridors, and towers. Water shaped it, but the result can seem almost built. The glowworm species seen at Waitomo is Arachnocampa luminosa, which is found only in New Zealand. That restricted range makes the cave's famous display even more distinctive. Visitors are not just seeing any glowing insect, but a species tied closely to one country and its cave environments. The cave was explored in the late 19th century by Tain Tinnerow and Fred Mace. Their exploration belongs to the human history of the site, when the underground world was being entered, mapped, and shared more widely. Such moments often turn local natural knowledge into a landmark known far beyond its region. Public tours began in 1889, making it one of New Zealand's early show caves. That early opening to visitors shows how quickly the cave's unusual beauty was recognized. It also means generations of people have encountered the place not only as a geological feature, but as a carefully guided experience. The Great Blue Hole is roughly 300 to 318 meters across. That broad width is one reason it looks so dramatic from above. It is large enough to read clearly as a circular void within the reef, making the contrast between dark central water and surrounding lighter tones especially strong. The hole is about 124 to 125 meters deep. That depth adds to the sense of mystery. A marine feature with that much vertical drop feels less like a shallow lagoon and more like a sunken shaft, reinforcing the impression that it is a true absence in the reef structure. Its almost perfectly circular dark center makes it visible even in satellite images as a geometric void in the reef. Geometric-looking natural forms often catch human attention because they seem almost too neat. The blue hole is one of those rare places where natural history produces a shape the eye reads as simple, bold, and nearly designed. The site is strange because it is both a cave and a sea feature, depending on the timescale you use. In one era, it was dry and air-filled. In another, it became flooded and marine. That layered identity is part of its fascination. Its current form makes more sense when its older life as a cave is remembered. In Cappadocia, the same landscape also contains rock-hewn churches and other human-made chambers carved into the soft rock. The softness of the volcanic material made it workable with tools, and that allowed people to adapt natural formations into shelters, sanctuaries, and interior spaces. The result is a place where geology became architecture very directly. Cappadocia's natural and cultural features are inseparable because people turned the odd geology into living space. Instead of building around the land alone, people built into it. That decision created a landscape where the boundary between natural form and human use is especially thin. It is one of the few famous strange landscapes where geology directly determined local architecture for centuries. The shape, softness, and arrangement of the rock influenced where people lived, worshipped, stored goods, and moved through the region. In this sense, the land did not merely surround human life. It actively shaped it. Mono Lake is an ancient saline lake with no outlet. Because water leaves mainly by evaporation rather than by flowing out through a river, salts stay behind and accumulate. Over long spans of time, this simple rule transforms the chemistry of the lake and gives it its unusual character. California State Parks notes that Mono Lake is more than 1 million years old. That age means the lake has had an enormous amount of time to accumulate salts, build ecological relationships, and preserve its identity through changing climates. Very old lakes often develop unusual chemistry and biology, and Mono Lake is a clear example. Because it has no outlet, salts and minerals have accumulated in the water for a very long time. This process is slow but powerful. Rivers and springs bring dissolved material in, and evaporation removes water without removing most of those minerals. Over time, the concentration steadily rises. Mono Lake is about 2.5 times as salty as the ocean and highly alkaline. That combination makes it a chemically extreme place compared with ordinary lakes. It changes what organisms can survive there and helps explain why its water, shoreline, and towers feel so different from more familiar freshwater settings. Mono Lake is strange because it looks barren and chemically extreme, yet it supports one of the West's most productive bird habitats. This contrast is part of its quiet beauty. The lake does not advertise fertility in the usual way, with lush vegetation or abundant fish, yet it is deeply important to migratory and resident birds. Some dune systems in Lensois marinensis extend for tens of kilometers along the coast. This long reach creates a powerful sense of repetition and openness. The landscape is not a tiny cluster of dunes with a few pools, but a vast system where sand and water patterns continue across great distances. The place is not a true desert because it receives far more rainfall than deserts normally do. This fact is key to its identity. It may look desert-like from above because of the sweeping dunes, but its climate does not fit the usual definition. That mismatch is one reason it feels so surprising. Utah State Parks says Goblin Valley is unlike any other place in the state. That statement reflects how unusual its combination of scale, form, and accessibility is. Many landscapes contain hoodoos, but Goblin Valley's dense field of small, figure-like rock forms creates a very specific atmosphere. The landscape is often compared to Mars because of its shapes and colors. The comparison does not mean it truly matches Mars in geology, but it captures the visual feeling of red-brown barren terrain, filled with oddly shaped formations. The valley seems otherworldly in a way that encourages planetary comparisons. The site's nickname works because many formations resemble crouched bodies or oversized stone toys. Human imagination responds strongly to repeated rounded shapes that suggest heads, shoulders, or postures. That is why the valley feels playful and strange, rather than simply eroded. Bisti lacks the dramatic green or blue colors of other strange places, relying instead on shape and texture. This makes it a quieter kind of weird landscape. Its power comes from subtle forms, layered rock, and the feeling of fragility rather than from bold color contrasts. Bisti feels especially remote because its strange formations are spread across open high desert rather than concentrated around a single landmark. That spread changes the emotional experience. Instead of arriving at one famous rock and leaving, visitors move through a broader field of oddity where the land keeps revealing new forms. Tsingy is strange because it turns soluble limestone into a landscape that looks dangerous even from a distance. Limestone is often associated with caves or smoother cast forms, but here it becomes sharp and severe. The rock seems less like shelter and more like a warning. The visual effect is closer to a shattered city skyline than to a normal mountain range. Dense pinnacles rising tightly together can look almost urban in silhouette, as if towers had been broken into sharp fragments. That resemblance gives the landscape a strangely architectural feel, even though it is fully natural. Dalvaza gas crater in Turkmenistan is a collapsed gas field crater that has burned continuously since 1971. That long-burning fire is what gives the crater its uncanny reputation. A brief industrial incident became a decades-long landscape phenomenon, turning a hole in the desert into an enduring source of flame. Similar basalt columns also occur on the island of Staffa in Scotland, which likely helped inspire old giant legends tied to the Giant's Causeway. This connection is fascinating because it shows how geology can shape storytelling across places separated by sea. When people saw these strange, columned rocks in more than one location, it became easier to imagine a giant-built path linking them. The legend may not be scientific, but it grew from real stone patterns that were unusual enough to demand an explanation. The Giant's Causeway is also a habitat area for seabirds and specialized coastal plants growing among the rock formations. That detail adds a softer layer to the site. It is not only an ancient volcanic surface or a place of myth. It is also a living coastal environment where plants and birds make use of the cracks, ledges, sea spray, and sheltered spaces created by the stone. Its folklore is so strong that many visitors first hear it explained as a giant-built road before they hear the geology. That says something important about how people relate to unusual landscapes. Before scientific explanation, the human mind often reaches for story. In this case, the myth survives because it matches the emotional experience of the place so well. The rocks really do look like the remains of some deliberate, oversized construction. The Richat structure sits in a desert landscape that otherwise lacks many obvious large-scale landmarks, which makes it even more conspicuous from above. In a region where the ground can seem broad, open, and visually repetitive, a giant circular formation becomes especially noticeable. Its distinct shape stands out more strongly because the surrounding land does not compete with it in the same way mountain chains or dense river systems might. Spotted Lake near Hosoyuz develops separate mineral spots as summer evaporation removes much of the water. This is the central rhythm of the lake. As warmth and dryness increase, water retreats and leaves behind concentrated mineral pores that separate into visible patches. The pattern is not fixed by walls or permanent divisions. It appears through seasonal loss of water, which slowly reveals the chemistry hidden in the basin. At Daylaw, vivid colors come from hot, acidic, salty fluids interacting with mineral-rich evaporite deposits. This means the ground is being painted, in a sense, by the meeting of heat, chemistry, and salt. When those fluids rise and spread, they leave mineral traces behind. The resulting yellows, greens, and oranges are not decoration, but signs of active surface chemistry in one of Earth's harshest places. Waitomo Glowworm Cave in New Zealand is a limestone cave system famous for its glowworms. That simple description already combines two different natural wonders in one place. First, there is the cave itself, shaped slowly by water dissolving limestone. Then there are the glowworms, living creatures that turn the cave into something far more than a dark underground chamber. Together, geology and biology create a place that feels gentle, mysterious, and unlike almost anywhere else. The Moeraki boulders on New Zealand's South Island are unusually large spherical concretions lying on Kokohi Beach. Their nearly round shape is what first captures attention. On a beach full of ordinary stones and sand, these giant spheres seem almost impossible, as though someone rolled them there on purpose. But they formed naturally inside ancient sediments and were later revealed by erosion. Some Moeraki boulders are up to about 2 meters high. That size is important because it pushes them beyond the scale of ordinary beach stones and into the scale of landmarks. A round rock that large has a very different presence. It feels less like a pebble made large and more like a geological object with its own gravity and character. Each boulder can weigh several tons. Their weight helps explain why they feel so solid and improbable. Even though they look smooth and almost playful in shape, they are massive bodies of stone. The contrast between their rounded appearance and their enormous heaviness is part of what makes them so memorable. Scientists explain them as calcite concretions that formed about 65 million years ago. Concretions form when minerals gather and harden around a center within sediment, gradually building a more solid body than the material around it. Over immense time, these hidden stone masses grew inside mudstone, waiting to be uncovered by erosion. What looks strange on the beach today began as chemistry inside buried sediment long ago. Antelope Canyon in Arizona is a slot canyon carved into Navajo sandstone. That means it belongs to a rock formation already famous for its desert beauty. But in this case, the sandstone has been cut into extremely narrow, twisting passages. The canyon is not wide and open like many river valleys. It is intimate, enclosed, and shaped into flowing walls that seem to wrap around the visitor. The canyon was shaped mainly by flash flooding and other erosional processes. Flash floods are sudden and forceful, especially in desert regions where dry channels can fill quickly. In Antelope Canyon, those bursts of water were the main sculptors. They cut downward, swept through tight passages, and smoothed the stone again and again over time. The rock belongs to the Navajo Sandstone Formation, which dates to the Jurassic. So the canyon is carved into very old rock, formed from ancient sand deposits that hardened long before the canyon itself took shape. This gives the place layered time. First, the sandstone formed. Then, much later, water began turning it into the narrow and graceful passages seen today. It is commonly called the door to hell or gates of hell. This name for Darvaza is dramatic, but it captures the visual impression well. A fiery crater in the dark desert naturally invites comparisons to mythic underworld images. The nickname is not scientific. yet it reflects the very real emotional effect of seeing fire burning inside a large hole in the earth. The crater lies in the Karakum Desert. Its desert setting is a big part of why the crater feels so strange. In a quiet, open, sandy landscape, fire becomes even more vivid. There is very little else competing for attention, so the glow of the flames stands out sharply against the darkness and emptiness around it. It is about 60 to 70 meters across and around 30 meters deep. Those dimensions make it large enough to feel substantial and dangerous, but still small enough that the human eye can take in the entire flaming cavity at once. It is not an endless burning field. It is a contained, intense wound in the ground. The usual story is that Soviet drilling punctured a gas-filled cavern whose roof then collapsed. Whether remembered precisely or in simplified form, this account is central to the crater's fame. It gives the site an origin in human industry, where the search for underground resources led unexpectedly to the opening of a fiery pit. Engineers are said to have ignited the gas to prevent dangerous methane from spreading. This is one of the most striking parts of the story, because it suggests that the flames were meant as a solution rather than a spectacle. Fire was used to manage an invisible gas problem, but the result became something far more lasting and iconic than expected. The fire was expected to burn out quickly, but it kept going for decades. That long continuation is what transformed the crater from an industrial incident into a global curiosity. A short-lived event might have been forgotten. A flame that keeps burning year after year becomes part of the identity of the place. Hundreds of gas flames can be seen around the crater floor and rim. This means the crater does not burn as one smooth sheet of fire. Instead, many separate flames flicker and dance across the interior, giving it a restless, textured appearance. The fire seems alive because it is spread across many points of burning gas. Darvaza is strange because it is partly industrial accident and partly enduring landscape phenomenon. That mixture is unusual. Some strange places are entirely natural. Others are entirely human-made. Darvaza belongs to the uncomfortable middle ground where human activity opened the door, but natural gas keeps the spectacle going. Few places on Earth feel as uncanny as a permanently burning pit in the middle of an otherwise dark desert. The uncanniness comes from contrast: fire and darkness, heat and night, activity and emptiness. The crater seems to hold onto energy, while the land around it remains quiet and still. The site sits below basalt cliffs on the edge of the Antrim Plateau rather than as a separate, isolated rock field. This larger geological setting gives the Giant's Causeway more depth as a landscape. It reminds us that the columns are not a random patch of stone, but one exposed part of a broader volcanic history written into the cliffs above. UNESCO recognizes the Giant's Causeway for both its scenery and its importance in understanding Earth's volcanic history. Some places are protected mainly because they are beautiful, and others because they are scientifically important. The causeway is both. It teaches while it amazes, which is one reason it remains such a powerful and lasting site. The Richat structure contains both igneous and sedimentary rocks. That mixture tells a richer geological story than a landform built from only one type of material. It means the region records both deposition and internal Earth activity, layering several different processes into the same circular structure. The structure is so large that it stands out best from space. Some landforms can be appreciated most fully only when distance reveals their pattern. On the ground, Richat is a desert landscape. From above, it becomes an eye, a ringed target, a visible signature across the Sahara. Pamukkale's white surfaces are mineral deposits left behind as hot water cools and loses dissolved carbonates. This process is delicate and repetitive. As the water changes temperature and chemistry, it can no longer hold all of its dissolved minerals, and those minerals settle onto the surface. That quiet process, repeated over time, creates the pale terraces. The site combines geology and archaeology rather than separating them into different zones. In Pamukkale, the land itself attracted human use, and that shared space remains visible. The terraces and the ancient city do not feel unrelated. They speak to each other across time. Lake Natron's shallow water, salt, and algae create dramatic tonal contrasts from above. This is why the lake often appears so striking in aerial views. Small changes in depth and chemistry become broad, visible patterns, giving the surface a painterly or abstract quality. The Danakil Depression is a rift environment where the crust is being pulled apart. That deep tectonic tension helps explain why the region feels so restless and unusual. Heat, volcanism, and hydrothermal activity are all easier to understand when seen as part of a crustal zone under strain. The White Desert includes chalk formations along with dunes, cliffs, wadis, and oasis features. This wider setting matters because it keeps the chalk sculptures from feeling isolated. They belong to a larger desert system, one that includes dry valleys, sand movement, and pockets of life. Chinese reds and other tones are locked into rock layers rather than added by plants. This makes the color feel more permanent and structural. Even when vegetation changes or disappears, the bands remain, because the history of color is part of the stone itself. The stone forest is scientifically important for understanding multi-stage karst evolution. The phrase may sound technical, but it simply means the place helps scientists study how limestone landscapes can change in several different phases rather than all at once. It is a record of repeated shaping. The cave at Waitomo contains a chamber known as the Cathedral because of its acoustics. This gives the cave a gentle second life beyond geology and glowworms. Sound lingers differently there, and the space invites quiet attention in a way that feels naturally ceremonial. Blood Falls emerges from beneath the glacier rather than from a rock face beside it. That hidden source is part of its mystery. The feature seems to leak directly from the ice itself, which makes it feel more secretive and less easily explained at first glance. The red stain is visible even in satellite imagery. Features visible from orbit often have a special kind of clarity. Blood Falls is not just a curious detail at walking distance. It is a mark large enough to be seen from far above, even in a landscape already famous for ice and emptiness. The Cave of the Crystals was discovered during mining operations in 2000. This is a reminder that some of Earth's strangest places remain hidden until human activity reveals them unexpectedly. Discovery can happen not through careful searching for beauty, but through routine work that opens a path into the unknown. Once pumping stopped, the cave system reflooded, making ordinary access impossible again. That gives the cave a fragile, almost temporary presence in human awareness. It was seen, studied, and admired, but then returned to a more sealed and inaccessible state. The Blue Hole became part of the Belize Barrier Reef Reserve System's protected areas. That protection matters because the sinkhole is not only geologically unusual, but part of a wider marine environment with ecological value. It belongs to a living reef landscape, not just to its own dramatic shape. Mass tourism and natural erosion both threaten Cappadocia's unusual rock forms. This fact adds a quiet note of impermanence. Strange landscapes may feel timeless, but they are often delicate. Soft rock can be worn by weather and by too many human footsteps. Mono Lake supports more than 300 resident and migrant bird species in its surrounding ecosystems. This wide variety shows that chemically unusual places can still anchor rich webs of life. The lake may seem stark, but the surrounding system pulses with seasonal movement and feeding. The lagoons of Lensois Maranhenses are most impressive after the rainy season, when they reach peak water levels. That timing matters because the landscape's most famous appearance depends on accumulated rain. The pools are part of a seasonal breathing pattern between dryness and renewal. Goblin Valley lets visitors walk among isolated hoodoos at ground level. This creates a feeling very different from viewing strange formations from a lookout point. The visitor enters the field of forms rather than simply observing it from outside, which makes the place feel more immediate and more personal. The Bisti Badlands formed from sediments associated with an ancient inland sea. So beneath the dry silence of the modern terrain lies the memory of long-vanished water. Ancient environments often survive in rock more clearly than in the imagination, and Bisti is one of those places where the present preserves the past in unexpected form. The surrounding habitats of Tsingy support rare and endangered lemurs and birds. That adds a living softness to a landscape that otherwise appears sharp and severe. Even among stone blades and difficult terrain, life finds refuge and continuity. Maori tradition explains the Moeraki boulders as cargo from the wreck of the canoe Araturu. This story shows how striking natural forms invite cultural meaning. The boulders were not only seen as unusual stones, but woven into a larger memory of voyaging and ancestral narrative. Upper Antelope Canyon is famous for beams of light when conditions are right. Those beams are brief and conditional, which is part of their beauty. They depend on sunlight angle, dust in the air, and the shape of the narrow canyon, so they feel like gifts of timing rather than permanent features. Reed Flute Cave still holds Tang Dynasty inscriptions dating back to 792 AD. These marks quietly connect modern visitors with people who stood in the same underground chambers more than 1,000 years ago. The stone remembers geological time, and the ink remembers human time. The dead trees in Deadvley did not rot away because the climate is so dry. But dryness turned ordinary decay into long preservation. Instead of dissolving back into the land, the trees remained as still silhouettes, allowing the place to hold onto its past in visible form. At Flygeezer, thermophilic organisms color the mound green and red. Life does not simply endure there. It actively shapes the appearance of the formation. Heat-loving microbes turn a mineral structure into a biological campus. Lake Hillier's color has changed over time and may change again with natural conditions. This makes the lake feel gentle in a different way. Even one of the world's most famous pink lakes is not fixed forever. Its beauty shifts with the living chemistry of the place. Badabi sad terraces formed as carbon dioxide escaped from mineral-rich water and carbonate minerals were deposited. This is a patient kind of construction. No loud force is involved, only slow release, quiet flow, and repeated settling. Over time, that softness of process built staircase-like pools in stone. And so the strangest places on Earth become quiet again in the mind, not as wonders to solve all at once, but as landscapes shaped by water, salt, heat, pressure, time, and life. Let them rest there softly now, like distant terrain under fading light, while everything grows a little stiller and a little more calm.